Hi, I'm Fabian Reiter, and in this video I will talk about a new way of measuring locality in distributed computing. But before we get to that, let me first tell you where I'm coming from. You see, I'm not really part of the distributed computing community. I'm more of an external observer who looks at distributed computing through the lens of automata theory and formal logic. What is that supposed to mean? I will explain, but in order to do that, we first need to take a little trip into classical complexity theory. Let me start with Fagin's theorem. This is a really nice result from classical complexity theory, but not too many people know about it. It basically says that there are two equivalent ways of defining the complexity class NP. On the one hand, there is the well-known definition based on Turing machines, and on the other hand, there's a more, let's say, obscure definition that uses logical formulas. I will not talk about this in too much detail, but let me give you at least a rough intuition. On the left, the Turing machine operates on a binary string, and on the right, I've represented the string as a relational structure, where each element represents a bit. Yellow elements are zeros and black elements are ones. And now let's look at this particular logical formula on the right. It says that there exists a binary relation R on the elements, and this relation must satisfy two conditions. First, R must be a bijective function, and second, this function must map yellow elements to black elements and black elements to yellow elements. Here's an example of such a function. So what does this formula tell us? Well, it just uses a complicated way of saying that the string contains the same number of zeros and ones. But more generally speaking, as soon as we have existential quantifiers over relations, we get a lot of expressive power. And that's basically because relations allow us to encode many useful data structures. And what Fagin's theorem says is that this expressive power is actually the same as what we get with non-deterministic Turing machines that operate in polynomial time. And even better than that, there's actually an algorithm that lets us translate between these two languages. Now, I thought it would be really nice to somehow extend this theorem to distributed computing, so that instead of a single Turing machine, we could talk about an entire network of machines. And conceptually, this is not very difficult. On the left, we have several machines that can send messages to each other over the network, and on the right, I've represented this network as a relational structure where some elements represent the nodes of the network and the remaining elements represent the input bits provided to each node. Now, given such a structure, we can again evaluate logical formulas like the one shown on the right. This formula says that the network is three-colorable. And more precisely what it says is that there exist three sets of elements C1, C2, and C3, such that for every element X, if X happens to be a node, then it is well colored in the usual sense. So this means that X belongs to exactly one of the three sets, and none of its neighbors belongs to the same set. Of course, this is just a very simple example. So now let me repeat this in more general terms. On the left, we have a network of non-deterministic Turing machines that run in polynomial time. And on the right, we have a logical formula that starts with a block of existential quantifiers over relations, followed by a single universal quantifier over an element X, followed by a formula that is local around X. So that means that the formula talks only about X and the elements in its nearest neighborhood. So conceptually, this is a rather straightforward extension of Fagin's theorem. It's basically just reproducing the original theorem for each node of the network. But from a more technical point of view, it's actually quite a lot of work to prove that it is correct. And that's because one has to deal with many low-level details. For instance, when one machine sends a message to another, the appropriate section of the sender's tape must be copied to the appropriate section of the receiver's tape. That's not difficult, but it's a bit like implementing an algorithm in assembly language. You know how to do it in principle, but you don't really want to do it. So in the end, it's a lot of work, but it boils down to a routine exercise that reuses many of the key ideas from Fagin's original theorem. That also means that by itself, this is not a particularly interesting result. In fact, you could even say that it's not a result at all. It's more like an exercise in reverse engineering, where I already knew more or less the kind of theorem I wanted, and only afterwards came up with the matching definitions on the left and on the right. So that's not a particularly interesting story to tell, but it can be the starting point of a more compelling story. And in the rest of this talk, I will show you how Fagin's theorem has led me to perhaps a new way of measuring locality in distributed computing. But first, I need to give you some context. Let me start by introducing one of the standard models of distributed computing. It's called the local model. In this model, we have a network of machines that all run the same algorithm. Each machine has a unique identifier and possibly some local input, and they communicate by synchronous message passing. This means that communication proceeds in a sequence of rounds, and in each round, every node exchanges messages with all of their neighbors. And more specifically, I'm interested in local decision, where the machines communicate only for a constant number of rounds and then have to collectively decide whether the network satisfies some graph property or not. If all the nodes say yes, the graph is accepted, but if at least one node says no, it is rejected. For example, this makes it easy to check if the graph is Eulerian. Each node simply says yes if and only if it has an even number of neighbors. So this particular graph is rejected because there are two nodes with odd degree that say no. Now, by itself, this model is rather weak. There are not too many interesting graph properties we can express this way. So to make things more interesting, we introduce Eve. She can have a look at the entire graph and then assign a certificate to each node. For instance, to check if the graph is three-colorable, we first let Eve choose a coloring and then let each node check that it doesn't have the same color as its neighbors. That's the case here. So this particular graph is accepted. Of course, there's an underlying assumption here. And the assumption is that Eve really wants the graph to be accepted. So as long as there exists a valid coloring, she will find it. Now, to make things even more interesting, we introduce a second protagonist who will play the role of the opponent. This is Adam, and his goal is to get the graph rejected. And now we let the two play a little game. First, Eve assigns colors to nodes of degree 1. Then Adam assigns colors to nodes of degree 2. And finally, Eve is supposed to assign colors to all the remaining nodes in a way that makes the entire graph well colored. But here, this is not possible. That's because Adam was clever. No matter what Eve tries to do, there will always be at least two adjacent nodes that share the same color. And so this graph is rejected. This means that although this particular graph is three-colorable, it is not three-round three-colorable because Adam has a winning strategy. However, if we take the same graph and just remove a single edge, then things become much more difficult for Adam. Again, Eve assigns colors to nodes of degree 1, then Adam assigns colors to nodes of degree 2, but this time, no matter what he chooses to do, there will always be enough free colors remaining for Eve to win the game. So this graph here is both three-colorable and three-round three-colorable, and that's because Eve has a winning strategy. And more generally speaking, we can consider games with an arbitrary number of alternations between Eve and Adam. And then we can classify graph properties according to the type of game that characterizes them. For instance, three-round three-colorability is what we call a sigma 3 property because it's characterized by a three-round game in which Eve starts. And classical three-colorability is a sigma 1 property because it's characterized by a single round game where only Eve plays. Similarly, you can of course also consider games where Adam starts instead of Eve, and for those we will use the letter pi instead of sigma. So that's the basic framework. But as is often the case, the devil is in the details I haven't mentioned so far. In fact, one has to be very careful not to give too much power to Eve and Adam, because otherwise everything becomes trivial. For instance, if Eve were allowed to give each node a map of the entire graph, including all identifiers, then the nodes could easily verify all graph properties locally. So, to keep things interesting, we must impose some restrictions. Now, of course, there are many possible ways of doing that, and actually there have been at least 3 papers that all impose slightly different restrictions on Eve and Adam. But in my case, I didn't really have much of a choice, and that's because I was guided by Fagin's theorem. So let's see how this compares to previous approaches. First, all the previous papers make the standard assumption that each node has a globally unique identifier. But in order to get Fagin's theorem, I had to allow identifiers that are only locally unique. By this I mean that nodes that are sufficiently far apart from each other can share the same identifier, like these 2 nodes here. Second, if the identifiers are globally unique, then one has to decide whether Eve and Adam are allowed to use those identifiers within their certificates. In the examples we've just seen, certificates were just colors, but in general they could be arbitrary strings that either depend or do not depend on the identifiers. And for the previous papers, this was an important choice they had to make. But in my case, the distinction didn't really matter because I allow identifiers that are only locally unique. So even if Eve and Adam were forbidden to use the existing identifiers, they could simply generate a new set of identifiers and then let the nodes verify that the new identifiers are indeed locally unique. Third, all the previous papers assume that certificate sizes can depend on n, the total number of nodes in the graph. But in order to get Fagin's theorem, I had to consider certificates whose size depends on the amount of information that nodes can see locally. And more precisely, the size of a certificate given to node V must be polynomial in the size of V's constant radius neighborhood. And finally, the previous papers assume that local computation time is either unbounded or dependent on n. But again, to get Fagin's theorem, I had to consider polynomial bounds with respect to the node's constant radius neighborhoods. So basically, the main difference with previous work is a much stronger focus on locality. And that was not a conscious choice, but rather a direct consequence of my attempt to reverse engineer Fagin's theorem. But now you may ask, what's the point of having Fagin's theorem anyway? Well, as I mentioned at the beginning, it gives us a way of translating between logical formulas and Turing machines. So imagine we have some questions about the local model, and suppose we are okay with the restriction to locally unique identifiers and local polynomial bounds. Then Fagin's theorem allows us to translate those questions to the world of logic to see if someone else has already done the hard work for us. So suddenly the local model is connected to a huge body of work that seems to have nothing to do with distributed computing. For instance, I use some major results about monadic second-order logic on grids, and also some classical results about finite automata and their connection to logic. By the way, don't worry if you're not familiar with these results. It's not really important to understand what they mean by themselves. What I'm going to focus on is the implications that they have on the local model. So, what can logic tell us about distributed decision in the local model? To see this, we must first define some complexity classes. Let's start with the class LP, which stands for local polynomial time. That's just a class of graph properties that can be decided without any certificates, so without any help from Eve and Adam. Building on that, we get sigma 1, which corresponds to single round games where only Eve plays, and similarly pi1, which corresponds to games where only Adam plays. And then by considering longer games where the two players alternate, we can build an entire hierarchy of complexity classes on top of that. This is of course very similar to the classical polynomial hierarchy, and in fact it's even a direct generalization of that hierarchy. You see, all of these classes talk about networks of nodes, but if we restrict them to networks that consist of a single node, then we get back the corresponding classes of the original polynomial hierarchy. So in particular, the class P is just LP restricted to single node networks, and NP is just sigma 1 restricted to single node networks. However, in the case of arbitrary networks, the problem of separating these complexity classes becomes easier. It's still not trivial, but thanks to Fagin's theorem, one can exploit separation results for monadic second-order logic to show that all the inclusions shown in red here are in fact strict inclusions. So this means that the hierarchy is provably infinite. As for the remaining inclusions shown with dashed lines, the question of strictness remains very difficult because these are in fact equalities if and only if P equals NP. This also means that from the point of view of distributed computing, the really interesting classes are those highlighted in yellow, because the other classes are basically just artifacts of the local polynomial running time. So what's inside the yellow classes? Let's look at some examples. In LP, we have Eulerianness. And this is actually a representative property for this class because it is LP complete under an extended form of polynomial time reductions. Then, one level higher, we have 3-colorability, which is again a representative property for that class because it is sigma 1 complete. And by the way, this can be shown via Fagin's theorem. Then a little higher in the hierarchy, we have Hamiltonicity. This is both LP hard and co-LP hard, but I don't know exactly where it lies in the hierarchy. I have only an upper bound of sigma 3 and a lower bound of sigma 1. And no matter how high we go in this hierarchy, we can always find more or less natural graph properties. For instance, at any level k, there is k-round 3-colorability. And this might even be a complete property for that level, but I haven't proved this, so that's just a conjecture. And finally, Fagin's theorem also allows us to show that some properties lie outside the hierarchy. And an example of such a property would be that the total number of nodes in the graph is a prime. Okay, but all of this may seem a bit abstract, so to make things more concrete, let me show you 2 examples of reductions I use to prove this kind of hardness and completeness results. I call them local polynomial reductions because they directly generalize the classical notion of polynomial reductions. Let's start with a very simple reduction. On the left, we have a computer network, and we consider the property that all nodes are blue. Intuitively, this is a rather simple property, right? And now we want to formally prove that this property is indeed simpler than another property. The other property being that there exists a Hamiltonian cycle. To do this, we let the nodes compute a new graph that is Hamiltonian if and only if the original graph contains only blue nodes. And when I say we let the nodes compute a new graph, what I mean is that they have to do this locally and in polynomial time with respect to their constant radius neighborhoods. For instance, the node on the top left in the original graph is responsible for computing the cluster of nodes on the top left in the new graph. Now, to see that this reduction is indeed correct, let's first assume that our original graph is a yes instance, like in the picture here. And now let's look at an arbitrary spanning tree. What we can observe is that this spanning tree corresponds to a Hamiltonian cycle in the new graph. This Hamiltonian cycle simply represents a depth-first traversal of the spanning tree. Conversely, if the old graph is a no instance, then there must be some node that is not blue. And it's very easy for that node to destroy the Hamiltonian cycle simply by adding an additional gadget to the new graph. So that's what I mean by a local polynomial reduction. And the nice thing about it is that if we restrict our networks to consist of a single node, then this is exactly the same as classical polynomial reductions. In fact, sometimes we can even take a classical reduction from a textbook and directly generalize it to the distributed setting. Let me give you an example. Here's one of these textbook reductions from classical complexity theory. We're given a Boolean formula in 3-conjunctive normal form, and we transform this formula into a graph that is 3-colorable if and only if the formula is satisfiable. You have probably seen this reduction at some point, but perhaps you have forgotten the details like me. So let me refresh your memory. The main point is that if this graph is 3-colorable, then 2 of the colors can be interpreted as the Boolean values true and false. And the third color represents a neutral value, which we will refer to as ground. And as you can see, for each variable we have 2 nodes representing its positive and negative occurrences. These 2 nodes have to be colored either true or false because they're connected to the ground node, and they cannot have the same value because they're also connected to each other. So one must be true and the other one must be false. And now look at this node at the very bottom. This is supposed to represent the truth value of the entire formula. And notice that it has to be colored true because it's part of a triangle where the other 2 nodes are colored false and ground. Now, of course, if we're given other formulas, we can apply the same reduction again. But suppose that each formula is given to a different node in a network, and suppose that we want to satisfy all the formulas in the network in a locally consistent way. By this I mean that adjacent nodes must agree on the values of their shared variables. So for instance, here the 2 nodes must agree on the value of P3 because they both have this variable in their formula. Now, if we want to enforce this requirement, we have to slightly extend the classical reduction. Currently, we have independent graphs for all the formulas, but we need to make sure that they are colored consistently. So we connect the false nodes to each other using a little gadget that forces them to have the same color. Then we do the same for the ground nodes and also for any nodes that represent shared variables. So here we also connect the P3 nodes. And that's it. Now the entire graph G' is 3-colorable if and only if the original graph G is satisfiable in the way I just explained. Again, this reduction can be computed by the nodes in local polynomial time. Each node is responsible for the gadget that encodes its own formula and also for half of each gadget that connects it to a neighbor. Now, this reduction may seem a bit artificial. In particular, the problem of distributed Boolean formulas may seem artificial. But it's actually quite useful because it's one of the building blocks I use to show that 3-colorability is sigma 1 complete. And basically, we got it for free. It's just a classical textbook reduction extended with a very simple connector gadget. Alright, but there's still something that may seem a bit unnatural. I keep mentioning that these reductions can be computed in local polynomial time. But the reason I insist on the polynomial part is just that I'm trying to replicate classical complexity theory. Yet people in distributed computing usually don't care too much about what's happening inside a single node. What they really care about is the communication between the nodes. So everything I've told you so far may seem like a nice little story, but it's not clear at all if this tells us anything meaningful about distributed computing. In fact, the hierarchy I just presented would be much more interesting if we could get rid of the polynomial bounds and just focus on communication. So let's do that. Here's a hierarchy very similar to the previous one, but this time we replace polynomial bounds with arbitrary bounds. This means that identifiers are still locally unique and certificate sizes still depend on constant radius neighborhoods, but now this dependency can be an arbitrary computable function instead of just a polynomial. So what happens in this more general setting? Well, quite conveniently, all the previous separation results carry over directly. So the hierarchy is still provably infinite. But this time, the dashed lines are honest equalities that do not depend on P versus NP. So this allows us to clean up the picture. We're left only with the yellow classes, and the hierarchy becomes a strict linear order. Additionally, if we slightly adapt the notion of reduction, again by dropping the polynomial bounds, then all the previous hardness, completeness, and non-inclusion results carry over as well. And I think this even holds for my conjecture about the completeness of K-round three-colorability. So this leaves us with an infinite hierarchy of complexity classes, and at least in principle, these can be interpreted as a measure of locality. On the lowest level, we have purely local problems, because here the nodes can only use the information they see locally. But the higher we go in the hierarchy, the more global information can be either proved or disproved by Eve and Adam. The main point that remains debatable is how meaningful each of these levels really is. And I don't have a definitive answer to that, but in the rest of this talk I will try to give you at least some intuition. But just before we get to that, I must mention a rather tragic twist in the story. You see, although most of the results from the previous hierarchy carry over to this general setting, there's one thing that gets lost in the process, and that's Fagin's theorem. So that's quite funny, right? This theorem was the starting point of the entire story. It guided the definition of the framework, and it was the main tool to prove most of the results on this very slide. And yet, it's the only thing that does not generalize to arbitrary bounds. Let me illustrate this with an analogy. Here's a picture I found on the website of a Swiss railway company. This was taken over 100 years ago, but I guess the photographer was not aware of one thing. They were taking a picture of Fagin's theorem. Can you see it? It's right there. It's this wooden structure upon which you can build a theory, and once you're done, you just remove the structure, but the theory remains standing. And now let me talk a bit more about this theory and how it might provide a way of measuring the locality of graph properties. And I think the best way to do that is to look at a few more example properties. Let's again start with a very basic example. We're given a graph, and we want to know if it contains at least one blue node. This is a basic property, but notice that it's not purely local, because nodes that are far away from a blue node cannot locally decide if the graph satisfies the property. So we need some help, and it seems like Eve could do something for us. Using her certificates, she could provide the nodes with a spanning tree where the root is a blue node. But the problem is, how can the nodes be sure that she's not lying? I mean, how can they know that they are really pointing towards a blue node? For all they know, the parent pointers could form a directed cycle. So the nodes need some proof that there is no cycle in the tree. One simple solution would be to let Eve add a distance counter to the nodes to tell them how far away they are from the root. And that's indeed an information they can verify locally. The root is at distance 0, and every other node is one step further away than its parent. However, there is still a problem. The size of these counters depends on the depth of the tree, and that's not possible with locally bounded certificates whose size depends on constant radius neighborhoods. So unfortunately, this simple solution doesn't work. And in fact, it's easy to prove that we really need Adam's help to solve this problem. So here's what we can do. Once Eve has chosen her spanning tree, we let Adam respond by choosing a subset of nodes. I will call these nodes the flipping nodes. And then Eve must respond by assigning a positive or a negative charge to each node while satisfying the following conditions. The root must be charged positively, and for the remaining nodes the charge must depend on their parent's charge. Normal nodes have the same charge as their parent, but flipping nodes have the opposite charge. Now, this may seem a bit arbitrary. How does that solve our problem? Well, suppose there really is a blue node like in the picture. Then Eve has a very simple winning strategy. First, she chooses an arbitrary spanning tree rooted at a blue node. Then she lets Adam choose any set of nodes, she really doesn't care. And finally, she just follows the instructions. That is, she starts with a positive charge at the root, and then she traverses every path from the top to the bottom, inverting the charge every time she encounters a flipping node. If she does this for every path, she wins the game. Conversely, suppose there is no blue node in the graph. Then Eve can try to cheat by providing a fake spanning tree that contains a cycle. But now Adam has a very simple winning strategy. He just chooses a single flipping node on the cycle. And no matter how Eve responds to that, she can never satisfy all the requirements. There will always be a pair of nodes on the cycle that detect an inconsistency, like here. And so Eve loses the game. Okay, so at alternation level 3, we have this rather basic property that there is at least one blue node in the graph. But what happens if we slightly change the objective and now require that there be exactly one blue node? Well, then this game here is not enough, because Eve can win even if there are multiple blue nodes. She just has to construct a spanning forest where each blue node is the root of a separate tree. How can we avoid this? Well, actually that's quite easy. In the last round, where Eve assigns charges to the nodes, we now require that she also tell everybody if the root is a flipping node. So that's just an additional bit of information that she must give each node. But it solves our problem. If there is exactly one blue node, then Eve still has the same winning strategy as before. But now, if there are multiple blue nodes, Adam has a winning strategy. Suppose Eve tries to cheat by constructing a spanning forest, like here. Then Adam can select just one of the roots as a flipping node, and Eve has no good response to that. No matter what she tells the nodes about the root, there will always be an inconsistency somewhere where two adjacent nodes see that they don't have the same answer. Great. So now we know how to express that there is exactly one blue node in the graph. And we also know that this property lies at most at level 3 of the hierarchy. That's still a pretty basic property, but in order to check it, we had to develop a protocol for verifying a spanning tree. And as usual in distributed computing, once we have a spanning tree, many things become possible. Let's look at a few examples taken from a very nice paper by Gus et Sumer. Let's start with the negation of purely local properties. For any property that lies at level 0, we immediately get that the complement property is at most at level 3. And that's because the negation of a local property is always of the form there exists some bad node where the property is violated. So all Eve has to do is construct a spanning tree that points towards such a bad node. Let's look at another example. If we are able to construct a spanning tree, then we can also easily check whether the total number of nodes in the graph is even. To do this, we simply aggregate modulo 2 counters from the leaves to the root. Each node checks that its value is 1 plus the sum of its children modulo 2, and the root also checks that its value is 0. But spanning trees allow us to do even more than that. For instance, a Hamiltonian path can be seen as a special case of a spanning tree where each node has at most one child. And if the root is also adjacent to the only leaf, then we even have a Hamiltonian cycle. And since these additional requirements are easy to check locally, this means that Hamiltonicity is also at level 3 at most. What about the negation of two-colorability? Well, a graph is not two-colorable if and only if it contains a cycle of odd length. So if Eve wants to prove that such a cycle exists, she can first highlight it in blue, then propagate a modulo 2 counter around that cycle, and finally construct a spanning tree whose root detects that the modulo 2 counter does not return to 0. Let's look at one final example. Level 3 also contains all properties definable in existential monadic second-order logic. And that's because Schwentig and Bartelmann have shown that such properties can always be defined by formulas of this particular form. That is, a block of existential quantifiers over sets, followed by a single existential quantifier over nodes, followed by some local first-order property that must hold everywhere. So Eve's job is to choose the sets S1 to Sk and to select a single node X. For S1 to Sk, that's easy. She just has to tell each node whether it belongs to that set or not. And to identify X, she constructs a spanning tree rooted at that node. Given the corresponding certificates, each node can then locally verify that it satisfies the local formula phi. Okay, so the main point here is that spanning trees are really useful tools because they allow us to express many natural properties. Now let's go back to the idea of measuring locality. Here's again the local bounded hierarchy, and now let's place some more properties on this scale. We already had Eulerianness at level 0 and 3-colorability at level 1. And as we've just seen, spanning trees allow us to place many natural properties at level 3 at most. By the way, one property I haven't mentioned so far is acyclicity, which lies at that level for the same reason as the others. We've also seen that spanning trees allow us to negate purely local properties, provided we're willing to pay the price of 3 additional levels of alternation. And this technique generalizes to the higher levels as well. For instance, since we know that 3-colorability is at level 1, we immediately know that non-3-colorability lies at most at level 4. And I also mentioned that some properties lie outside the hierarchy. I proved this for cardinality-dependent properties like having a prime number of nodes, and I suspect that the same proof could be adapted for other properties like having a non-trivial automorphism. By this I mean an isomorphism of the graph to itself that is not the identity function. But I haven't done this formally, so it's just a conjecture. Alright, so now the big question is whether this scale really captures our intuition of locality. I think most people would agree that Eulerianness is a purely local property. Each node just has to verify that its own degree is even. And I think it's also somewhat intuitive that having a non-trivial automorphism is a very global property. After all, the automorphism may have to map very distant parts of the graph to each other. But what about all the levels in between? For instance, would it make sense to say that Hamiltonicity is a more local property than non-3-colorability? I don't know about you, but I have no intuition about that. So it would be nice to have some benchmark against which to compare this classification. And luckily, such a benchmark already exists. Here's a very different hierarchy of complexity classes which was introduced by Goes and Surmiller. They call it locally checkable proofs. So how is this different from the yellow hierarchy on the left? Well, remember that the yellow hierarchy is based on alternation between Eve and Adam. And its main constraint is that certificates must be locally bounded. Now in the green hierarchy on the right, there is no alternation, there is only non-determinism. So Eve has to play all by herself. But here she's given more power. She can use globally unique identifiers, and her certificates can be much larger. In fact, instead of imposing local bounds, this hierarchy measures how large Eve's certificates must be to verify a given property. And the certificate size is measured with respect to n, the total number of nodes in the graph. Now, why am I talking about this hierarchy in particular? Well, that's because Feuillée suggested that this may also be a measure of locality. Again, the lowest level is local by definition. And as soon as we allow certificates of polynomial size, everything becomes trivial, because then Eve can just give the nodes a map of the entire graph. So the highest level is global simply because it contains all graph properties. And more generally, Feuillée's intuition is that certificates are pieces of global information that Eve can give to the nodes. So the larger the certificates, the more global information the nodes can receive. Okay, so now we have two potential measures of locality. How well do they agree with each other? Well, they both agree that Eulerianness is purely local. But that's not really surprising, because the lowest levels are defined very similarly. So let's go a little higher. Both measures also agree that 3-colorability is very close to being local. But again, that's not particularly surprising, because the power given to Eve is similar in both cases. On the left, she's allowed locally bounded certificates, and on the right, she's allowed constant size certificates. For many natural graph properties, this doesn't make a difference. So what happens at higher levels, where the definitions of the two hierarchies start to diverge considerably? Let's look at the properties we placed at level 3 on the left. Remember, we did this using spanning trees. Now in the right hierarchy, these properties all fall into the logarithmic class. And that's because logarithmic size certificates allow Eve to encode a spanning tree. And by using globally unique identifiers, she can also convince the nodes that her spanning tree is correct. Now let's go to the very top. As I said, I conjecture that the left hierarchy does not contain the property of having a non-trivial automorphism. So that would classify it as a maximally global property. And again, the right hierarchy agrees. Gös and Surmailer have shown that if Eve wants to certify a non-trivial automorphism, there's nothing intelligent she can do. She basically has to encode the entire graph in her certificates. So it almost seems like these two measures of locality are in perfect agreement. But that would be too good to be true, right? And unfortunately it's not. Remember that in the left hierarchy we cannot express that the number of nodes is a prime? Well, in the right hierarchy this is already possible at the logarithmic level, and it can be done in exactly the same way as expressing that the number of nodes is even. We construct a spanning tree and then aggregate counters from the leaves to the root. The reason this doesn't work in the left hierarchy is just that locally bounded certificates are too small to contain the counter values. Conversely, I've mentioned that in the left hierarchy it's relatively cheap to negate properties. It costs at most 3 levels of alternation. This allowed us, for instance, to place non-tricolorability at most at level 4. But Gös and Surmailer have shown that the same property requires almost quadratic size certificates in the right hierarchy. So there it's almost maximally global. So this leaves us with two potential measures of locality that agree on many things, but not on everything. Where do we go from here? Well, I don't have a clear answer to that, but perhaps the entire notion of locality is a bit too vague to be precisely captured by a single formalism. No matter what formalisms we come up with, there may always be some arbitrary aspects to them, like counting being extremely difficult in the case of the left hierarchy, or negation being extremely difficult in the case of the right hierarchy. So perhaps the best we can do is to come up with even more measures like these, compare them, and then focus on the aspects on which they do agree. Thanks for listening.